Hi everyone, Quiveen here from the comfort of my kitchen. In today's video, we will look at a couple of different things, but firstly, we will look at the two different kinds of day that we can use to measure how things move in the sky. The first one, the most familiar one, is the solar day. It is the day that we normally use for our earthly activities. So we can see here that the sun is directly above the south. It's midday, physical, local midday. Down here on the clock, it says it's 1:30. That's because we are after changing the clocks by an hour thanks to daylight savings time. Ireland is currently using daylight savings time, so the sun will get above the south an hour later than we might normally expect. The sun does reach directly above the south a little after 12 o'clock here in Ireland because we use the same time based in Greenwich in London, Greenwich Mean Time, which is pretty much the same as Universal Coordinated Time. It just means that our physical midday is a little delayed because we use the same midday as the physical midday in London. And then when we add an extra hour for daylight savings, it gets pushed ahead even more. But if we look at the sun here directly above the south, and if we hop through a couple of solar days, we can see that the sun's position does change slightly, gets a little bit higher in the sky. If you go back and watch my video on the analemma, you'll also know that the sun is moving in a little bit of a figure of 8, drifting slightly from side to side as it moves up and down. It's a tough phenomenon to notice, but you might be able to see here that the sun ends up a little bit before the south, just as we come back to midwinter, and then ends up a little bit ahead of the south as we move past it. So the analemma, which I went through in a previous video, it does slightly change the position of the sun a few minutes off of what you might expect on different times of the year. It's partly because we are moving around the sun. Our motion around the sun is also what causes the two different kinds of day. A solar day measures how long it takes for us to turn around until we are facing the sun again. If you put a mark on the planet Earth and you wait until the sun is directly above the south from that mark, the time from the sun being directly above it at one midday to it being directly above it the next midday is roughly 24 hours. Our day isn't exactly 24 hours, but the solar day pretty much is 24 hours, and that's what we normally base our clocks on. So we can see here with the atmosphere removed, we've got a bunch of planets there out to the side of the sun. Saturn, Mars, Mercury, Uranus, Jupiter, Venus, Neptune is out there somewhere as well. And we still have that comet at 12P Pons Brooks. If we move through our solar days here, the planets, of course, orbit around the sun. The sun appears to stay in pretty much the same place, but the stars do not. We turn around to face the sun while we move around the sun. So every day we've moved a little bit further around the sun, and that means we need to turn a little bit further for the same part of the Earth to be facing back towards the sun directly. If you were just looking at the Earth spinning in space, we can turn around until we're facing the same direction out into the Milky Way in a little bit less than 24 hours. And Aldebaran should be a good example for that. So there we go, Aldebaran, the brightest star in Taurus. Here on the 31st of May, we can see it's pretty much directly behind the sun. And you can see over here is Orion. This is why we're not really seeing Orion anymore. It's pretty much, in the same part of the sky as the sun. So we won't really get to see it for a while. If we lock onto Aldebaran here, just to make sure that we keep seeing it. And if we, instead of moving through solar days, move through sidereal days, if we wait until the Earth is facing back to Aldebaran again, you will see that the sun now appears to be drifting to the side while the stars appear to stay in the same place. And the truth is the stars do stay in the same place. Even the sun does. But we're moving around the sun. We're not moving around these other stars. The same way that a solar day is measured by counting how long it takes for a given part of the Earth to turn around until it's facing the sun again in the same part of the sky, a sidereal day is measured by how long it takes us to turn around to face back to a more distant point. We can essentially treat the stars as fixed points in the sky, given that they are so far away. Of course, our orbit around the sun means that we travel, 2 AU pretty much from one side of the sun to the other side of the sun, with the sun in the middle and AU from either extreme. We travel a pretty far distance as we move from one side of the sun to the other. So that can cause a little bit of wobbling with some stars, parallax, which we can use to measure how far away different objects are. We can see here, as we move through sidereal days, after a few sidereal days, the Earth is pretty much into nighttime. It only takes us, 20 odd hours to turn around until the same part of the Earth is facing a distant star in the sky. Because the Earth has moved around in its orbit, we then have to turn a little bit further before the sun comes back to the same place it was the day before. So this means that the solar day is a little bit longer than the sidereal day, because the solar day isn't just about the Earth turning around, it's about the Earth turning around while it's orbiting the sun. So we have to turn a little bit further. The actual length of time it takes for the Earth to just rotate 360 degrees is closer to the sidereal day than the solar day, because we have to turn just a little bit more than 360 degrees to realign ourselves with the sun, because we're after moving further around it in our yearly orbit. So that's the difference between a solar day and a sidereal day. I didn't explicitly mention solar or sidereal days in the previous video, but if you go to quivinscontent.ie, where I do a little write-up of every video after I post it, I do mention the sidereal and solar day in that one, because it has to do with the position of the plough and the North Star. Of course, the North Star is going to stay above the north. If we move through solar days, it will appear that the plough is moving around the North Star. If we move through sidereal days, they don't really seem to move at all. The stars, of course, aren't really moving. It's the Earth that's rotating. And if we move through, hours or minutes, our rotation will show that the stars are moving. But the whole point of a sidereal day is that the stars are in the same relative position. We turn around until the stars are in the same place. That's the Earth actually turning 360 degrees. As I mentioned, we need to turn just a little bit further in order to get the sun back into the same position in our sky. So we're going to move just a couple of days into June, because as I mentioned, we've got a bunch of planets there next to the sun. So we're going to head back to sunrise. Here we go. We are looking at the sky with no atmosphere here. That's how we were able to see the sun and the stars in the sky together. That, of course, is going to give you a perfect, flawless view of the Milky Way. If you can get up above the atmosphere, that is really the best place to see it. Unfortunately, that is much easier said than done. If you're an astronaut, you'll have that unrivaled view. If you are a space tourist, it really depends how far up your rocket goes. To really get a clear view, you do need to be outside the atmosphere. So we can see there's a bunch of planets in a row. Neptune is out here somewhere, so if I zoom in, it should highlight itself. There we go. There's Neptune, a little bit closer to Saturn than it is to Mars in our view here. Technically, Neptune is closer to Saturn than it is to Mars, but it's hundreds of thousands of kilometers away from either of them. Saturn and Mars are much closer together than Saturn and Jupiter, or Saturn and Mars, even with the whole planet Jupiter's orbit occupying the intervening space. Uranus, as I've mentioned, I think many times, it's not quite visible to the naked eye. Here, under these flawless, hard to replicate conditions, you might just be able to see it, but even in a pristine dark sky here on Earth, it's going to be a little tougher to see. And with the atmosphere back, the light of the sun is scattered in our atmosphere, glowing yellow and then scattering into blue. They're gone. The planets have vanished. It's just too bright. Now, I do believe we're looking at the sky here from the city, so let's push out to the countryside. Still nothing. Let's get a little bit back, a little bit closer to sunrise. There's Mars and Saturn. We can absolutely see those. So out of the 8 planets that should be visible, that are above the horizon before the sun rises, we only get to see 2 of them here in Ireland. Venus is right there by the sun. If we take a closer look in here, we should be able to see it, well, just on the far side of the sun, but you can see the S of Venus just there. If you were closer to the equator, you might have a better chance to see this parade of planets, as people are calling it. Jupiter and Mercury would look very nice in this close conjunction, but it's not possible to see from here in Ireland, or really many northern latitudes. Even if you are a bit closer to the equator than we are here in Ireland, let's go down to the west coast of the United States here. I'm not very good. Well, Annandale is there, so I can't be too far away from Washington, D.C. I know that they're reasonably close together. And by reasonably close together, again, I do not know much about the geography of the United States. If we move ourselves to sunrise here, With all of the atmosphere taken away, of course, it's certainly achievable. Let's get the sun under the horizon. And again, we're still looking at this view from the countryside, the best conditions we can get. You can kind of see, well, we're probably seeing Jupiter rather than Mercury, but yeah, just about. If you're in the countryside that far down the planet, a little bit closer to the equator, they might just about be visible. I do not want to underemphasize the difficulty of actually seeing these 4 planets in a row, because the sun needs to be so close to rising for Jupiter and Mercury to be above the horizon. They're very likely to be blocked out by the glow of the sun unless you are close to the equator and viewing it under good conditions. If we push just a little bit further ahead, well, of course, when the sun rises, everything disappears. But we can see that Jupiter and Mercury are going to stop being visible just about here, which isn't very high above the horizon. So you do need to be out in the countryside, not in a built up area, up on a mountain, and at least, I would say pretty much at least this close to the equator. So we're talking, around the Mediterranean here in terms of latitude. It will be very difficult and impossible for us here in Ireland. We're just not going to be able to see it under normal conditions. But if you're in another part of the world, you might just get to see 4 planets in a row. It will be tricky. You don't get to see Neptune and Uranus without a telescope, but you might get to see 4 at least. So I hope that if you are in another part of the world, you get to see that. If you're not, I hope you enjoyed my description of the difference between a sidereal and a solar day. As I mentioned, you can also head to my website, queebeanscontent.ie, to look at a review of this information. If you would rather watch videos about astronomy, then I put up new ones twice a week, so you can subscribe to this YouTube channel so you're more likely to be notified for when the next one goes up. I hope you do subscribe and like this video if you enjoyed it, and either way, I hope I will see you back here next time.